So thanks very much, and thanks for being here. I'm going to discuss today, it's kind of a mishmash of things, a little bit of case study in architecture, a little bit about how we started using Erlang in a fairly large scientific organization, and I'll even throw a little bit of neutrino physics in there. So what you're looking at here is a picture of what's called the Sudbury Neutrino Observatory. This is the first detector that I worked on, and one of the two detectors that I know Erlang is deployed on now. It's a huge underground ball of extremely sensitive detectors, basically. So this particular picture is taken in a cavern 2 kilometers underground in Sudbury, Ontario, in a nickel mine. If you sort of squint down at the bottom right, you can see a couple of people. This detector is 10 meters in diameter. Each one of the little, I don't know how well you can see, but there's essentially, if you look, you can see a bunch of little, what look like little white cylinders. Each one of those white cylinders is the base of a device called a photomultiplier tube, which is an exquisitely sensitive detector which is capable of resolving even a single photon hitting it to produce a really macroscopic charge. This detector is used to study some of the fundamental properties of neutrinos, and because of its remote location and its very high demands on performance, it just so happens that Erlang was a really great fit for running it. So before I get into exactly why that is and how we went about deploying Erlang to this experiment, I want to talk a little bit about neutrino physics to sort of motivate why we're doing this in the first place. This picture is essentially the simplest pictographic description of what's called the standard model of particle physics, which essentially is a complete theory which describes all of the known forces and matter in the universe. Up at the top left, you've got your quarks. Quarks are particles, subatomic particles, which make up the protons and neutrons, which you find in the nucleus of an atom. Off to the right, you have your force carriers. These are bosons, are what they are called, which mediate forces, like a photon, which mediates the electromagnetic force. There are gluons, which are strong force. If someone can figure out how to do it, there is a graviton that belongs in there that would mediate the gravitational force. And then in the bottom left, you have the leptons. These are fairly familiar components of matter, like the electron, which I expect most people will have at least heard of, is a lepton. In the center of it all is the Higgs boson, which has gotten a lot of press recently. Some people call it the God particle, which is just sort of a tongue-in-cheek way to describe it. The Higgs boson is the particle which is responsible in the standard model for giving everything else mass, which makes it obviously a very, very interesting particle and sort of the linchpin of the entire theory. What else is interesting, though, is it turns out that the neutrinos kind of stand out, and they are the second row of this little picture in the bottom left. It turns out that the Higgs boson gives mass to everything in the universe except neutrinos. Something funny is going on with neutrinos that we don't fully understand, and it makes them a really interesting target of study. So even though we have now discovered the Higgs and we've sort of nailed the final nail in this coffin of what gives mass to things in the universe, it turns out that the neutrinos are simply not the case. You still have work to do there, and so they're a very interesting target of a lot of study. It turns out that that weirdness does not end there. If you have a particle traveling in air, for example, electron, proton, whatever, it turns out that in general you need only sort of a few centimeters of material to just stop it cold. It turns out that for a neutrino in this incredibly complicated and sophisticated graph here, if you think of the neutrino as this little blue dot on the right, the equivalent amount of material you need to stop it is about 1 light year of lead, which is roughly the distance from here to the nearest star, or 6 trillion miles, roughly. So that's already something that's extremely peculiar and worth thinking about. The other very bizarre thing is that it turns out that they have a mass, but it's an extraordinarily small mass. So it turns out we know the electron, for example, weighs 500,000 electron volts, which is a unit that we like to use in physics. The neutrino weighs somewhere in between 40 thousandths of an electron volt and 2 electron volts, which is extremely small. To put that in perspective, if I were to put the neutrino, so the neutrino mass lies somewhere in between these 2 red bars. If I wanted to put the electron mass on the same scale, it would be 30 miles that way. And that's extraordinary because most of the particles that we know, they're not separated by that kind of a gap. There's maybe a factor of 10 or 100 between a particle and its next heaviest particle. So something very weird is going on with neutrinos. The saving grace of studying them, because it's obviously incredibly difficult to study something that you need a light year of lead to stop, and they're so small that it's not like you can really take them and just put them on a scale. The saving grace is that they are as numerous in nature as they are reluctant to interact with the rest of it. So even though they interact extremely rarely, the sheer number of neutrinos that are present in nature means that every now and again, one of them will stop in a reasonable distance. So if you had, the number that I like to throw around is if you had a dollar for every neutrino that was passing through your body, you could pay the United States national debt 10 times every second. But in your lifetime, one of them maybe will stop in your body. So obviously, when you're talking about numbers this big, it's really hard to wrap your head around that, but that gives you kind of an idea of the sheer number of neutrinos that exist in the universe. So in order to feasibly study these things, you need to build really large detectors because you need a lot of mass to stop a neutrino and actually be able to study it. You need many, many, many I/O channels because in general, the events are not only rare, but they're very weak. And as a consequence, the signals that they produce are small. And you need to make sure that you capture essentially all of the energy that is released in those interactions. So you need a large detector, which is just absolutely covered in instrumentation. They're extremely rare events, as I mentioned. So in SNO, for example, SNO+, which is the detector I showed at the beginning, despite the fact that it's 10 meters in diameter, you may have 10 or so events per year. And because they're so rare, it's important that these detectors be well shielded from the environment, anything that may mimic a signal. So you need to basically bury them, which is why that one, for example, is, like I said, 2 kilometers underground in a nickel mine. They're also really cool to work on because making measurements of this type really requires that you are on the absolute cutting edge of technology and science to be able to actually reconstruct what's going on in these incredibly rare events and make conclusive predictions. So what this detector would actually look like, I showed you the original picture. This is kind of a very schematic representation of what it would look like underground. That giant sphere in the title slide is, again, this sphere here. Above that sphere, there's an area called the deck. And the deck is where we basically have all of the support hardware that runs the experiment. So on that deck, if you go on the deck, what you see is a number of all sorts of different systems for monitoring pressures, to carry liquids into the detector and out of the detector. And in particular, one of the things you notice are there are these huge racks of electronics on the top right corner. It's a little hard to see, but if you look carefully, you can see that there's essentially rows upon rows of cards. So each crate, there are these racks and 2 crates within each rack. Each crate has 16 cards in it, and each card has 4 daughter boards. And the cards themselves are essentially, they have a number of Xilinx FPGAs on board that are programmed in VHDL, which are responsible for controlling the photomultiplier tubes. Each of the daughter boards then is sort of an interface to 16 of those. So you have 16 channels per daughter board, 4 daughter boards per card, 16 cards per crate, and you have something like 50 crates, which are all full of electronics. So understanding a physics signal that's coming from your detector requires having a precise understanding of the state of this hardware at any given time, which is not a small task given how complicated it is. Slightly even more complicated than the hardware setup is the software setup. So this is an incredibly heterogeneous group of tasks that are all cooperatively acting to try to take data and control the experiment. You have the data acquisition software is written in Objective-C. That communicates directly with the cards that I just showed you in the last slide, which we call them the XL3s. Those are written in a combination of a dialect of C and hardware description language. Then physics data is basically streaming through those XL3s over to a thing which we call the event builder, which basically just packages all the physics data that it's seeing and turns it into an event. That's written in C++. Now, the event builder barfs out those events into analysis programs, which are also written in C++. And in order for the analysis programs to make sense of that data, they need to communicate with essentially or understand precisely what the state of the hardware was at the time that the event occurred, which means you need some logging infrastructure to be able to communicate with the boards themselves. Now, those are typically written in very high-level scripting languages like Python, and the data is stored in a Postgres database. So in addition, there are then monitoring tasks which are used for real-time analysis of the state of the hardware, which are written in Python or Perl or whatever the detector operator's favorite language is, basically. So you need some system in the middle here, this control block that I've thrown up there. You need some system which is capable of interacting with all of these different pieces simultaneously to present a consistent state of the hardware so that you can actually perform a physics experiment. So the requirements for this thing are fairly straightforward. You need something which will fail in a very graceful way and restart in an even more graceful way. This detector is, as I mentioned, it's 2 kilometers underground, and you have something like 6 to 8 hours of access per day to actually go down and work on the detector. So if something fails while you're not there, you're stuck with it. There's no way to go down and fix things.
Do you mind if we ask questions while you're going through this?
Please, go ahead.
Can we back up?
Sure. To?
The slide right before this one.
Uh-huh.
So the builder, you said, packages up events.
That's right.
So taking raw data, and does it actually try to detect an event at that point? Or like,
no, so. Sure, yeah.
And one other thing, because I think it goes into that. Do you have to deal with false positives?
All the time. And actually, those two questions are almost the same question, it turns out. When you have, so everything around you is radioactive, right? Even the materials that are used to construct the detector are radioactive. And what you're trying to detect is very weak radioactivity in the detector. So I said, oh, there are only tens of events, but those are neutrino events. The non-neutrino events, that can happen at rates of sort of tens of kilohertz or even up to megahertz, where you have essentially the photomultiplier tubes are just being lit up constantly. And so the stream of data coming out of the XL3s is huge. It saturates our network links, no problem. And then it is up to the builder, essentially, to aggregate those events, decide which one of them fit together, and construct some coherent event out of it that is worth looking at. So there's a series of essentially Boolean cuts that you have to pass. Was it this many photomultiplier tubes going off or more? If I try to reconstruct how energetic the event was, is it above this number? And so on and so forth. And if something passes all of those cuts, it becomes an event that gets passed on for real analysis.
So it's actually doing it's going through a logical tree?
Yes. So there's event.
Doing like pattern detection?
No, there's an event, there's real event selection, and some of the events, some of them are you can really use pattern recognition to get away with, but that's not common in this particular experiment.
Thanks.
Sure. So as I mentioned, you need it to be a very graceful system. It's underground. It's 2 kilometers underground. It's connected to the outside world by a single fiber, which runs up a mine shaft. That gets broken all the time, and so you need a system which is capable of failing in a way so that things are safe. You also need, as I mentioned, easy interoperability. It's incredibly important that you be able to interact with this system from a number of different environments and languages. You need it to be powerful enough, even though it has a very high-level interface, you need it to be powerful enough to twiddle bits on embedded hardware, because that is a large subset of what you're working with. And you also really ideally want a paper trail. When you're dealing with complex hardware setups like this, oftentimes you find that your hardware will fail in a particular state, It may be that state, or it may be the chain of events which led you to that state which caused the hardware to fail. So it's nice to be able to reconstruct precisely how you got there as well as where you were when hardware failed. In our case, we decided to solve this problem with single board computers. So there's a company called Acromag. They make a lot of dedicated hardware. This, in particular, we used a product of theirs, which is single board computers with basically field I/O points. So this picture up in the top right, there are 4 slots on the bottom of that device. Each one, there's a little card that fits into that slot, and then you have a nice jack on the front that you can plug into. Each one has either an analog to digital converter in it, or a digital to analog converter, or digital I/O. And each one provides something like 24 channels of I/O. So you have 24 channels times 4 cards per little single board computer. This was really nice for us because it lends itself very nicely to a very simple protocol. All you're doing is you're either reading or writing from one of 24 channels on one of 4 cards. So you really only need sort of 2 bits to specify an operation. You need another 2 bits to specify which card. You need basically a 24-bit bit mask to decide which channel you care about. And then there's sort of an optional blob at the end which tells you may want to configure something, set the gain, for example, of a channel. And so that's all contained in that payload. It's very, very simple. And so when we came time to actually implementing the software system that would control these things, I said, let's use Erlang. This is a great case. We need a really robust system that is deployed in a remote environment where failure is not really an option. We need it to have both high-level and low-level characteristics that we're able to use to our advantage. So when I brought this up, the response was fairly straightforward. People basically looked at me like I was crazy and said, what are you talking about? The physics community is very much a C community. Like virtually everything is written in either C or C++. Python is like really the new kid on the block in the physics community. So that's sort of where we are in terms of the chronology of programming languages. And so the idea that we would not use...
Is Fortran still there?
Oh yeah, Fortran's absolutely still kicking around, yeah. And some people are even using Fortran 90 now, which is a big deal. So yeah, there's a lot of legacy languages kicking around. People are not really comfortable with new technologies, in particular because if they didn't write it, then there's absolutely no way that it could be correct. And so new languages are very weird and mysterious. But I really wanted to use Erlang, and so I was just looking for an excuse, and I got a great piece of advice, which I'm glad I got at the time, which was basically, it's much better to beg for forgiveness than to ask for permission, so just do it. Develop a prototype, show that it can work, show that it has the features that you want, and go ahead. So what I ended up doing was basically using Web Machine and ports. Each one of those channels was mapped to a unique URI in the web server. And then if you wanted to get the value of a particular channel, you would simply issue a GET request on that particular URI, and you'd get back a JSON formatted document. If you wanted to change the value of something or write to a particular register, you would post to that same URI, and you could accomplish it that way, and you'd get back a JSON formatted response. It worked extremely well, and the nice thing was you got a very simple fixed layout that for the hardware, because it's, you have 4 cards and 24 channels per card, which was great. The sort of killer demo that I gave was you would have this a Python script, which basically was just pushing random numbers into the server, the web server, and causing a bunch of LEDs to flash. And you'd log into the little single board computer, which was running Linux, look for which process was flashing the LEDs, and just kill -9 it. And what would happen is people would say, okay, well, what's the big deal? And you'd say, well, the lights are still flashing. It's, okay, so nothing happened. But then when you look at the process table again, it has a new process ID. And then when you say what happened was I killed that process, but the Erlang runtime system restarted it so quickly that the Python script didn't even know that the server was down. They were pretty much sold at that point. There's not much better demonstration you can give than something that is resilient to a kill -9 in Linux. So that worked really well. And after being deployed, I can say that we have literally 100% uptime. This system has never gone down and has never been down for maintenance or any other reason. So it's an incredible success. So what happened was, on the good side, we had, like I said, fantastic uptime, literally 100%, excellent interoperability. Yeah, go ahead.
Over what time frame?
It's been in deployment for 4 years now.
Wow.
Excellent interoperability in terms of just being able to just fit right in, and obviously it's just HTTP. So if you can do HTTP, you can talk to it. And it was a great management success from the standpoint that when we started, everybody sort of looked at me weird when I said Erlang, and at the end of it, I think people were sort of coming around to the idea that this was really a great language for this sort of thing. There were bad sides too. I was the only, and am the only, Erlang developer for that collaboration. Sorry? Yeah, you'd think that would work, right? But it was basically, they were left with a system that was difficult for them to modify, and luckily they didn't really end up needing to, but when they did, or when they wanted things to be modified, it was just tough for them to get it done. It turns out that having a really static configuration where things really never change, I thought that would just make things so easy, and it's not easy. It turns out that doesn't make things a lot easier. You had these static configuration files, and it was difficult to work with because if you wanted to change anything, you really needed to log in, stop the server, change the configuration file, start the server again, and wait to see if you screwed anything up, which, at the time didn't seem so bad, but with the system that I'll describe next, which was sort of the next iteration of this project, it just seems like absolutely medieval. And also the fact that there were protocols within protocols here, which made it difficult to understand exactly how data was moving through the system. So you would post JSON to a web server, which then would translate that to a binary protocol, which went over a port. The port then translated that binary protocol into its internal format. That called some C. The data came back, got translated back into the binary protocol, back to Erlang, which got turned into JSON and came back to you. And it was just difficult to figure out exactly how data was flowing and where you could get tripped up. And then there was, of course, the terrible, really terrible things. There was no real possibility of service discovery with this particular application. So if you wanted to know what cards were installed, what they did, what they were connected to, you're pretty much out of luck. There was just Excel spreadsheets around that told you this card, this channel was this. And so if you rewired it, you would have to go and edit a spreadsheet somewhere, and God forbid that you get an old spreadsheet or someone forgot to edit the spreadsheet, because you would have to essentially get deep into the bowels of this detector to actually figure out what's connected to what. And it was extremely inflexible for the same static configuration reason I mentioned before. You couldn't just change something. That was not an option. You really had to stop the whole system, change some variables, edit a spreadsheet, and so on and so forth. So it was just kind of a mess. And that wonderful paper trail I was talking about was rendered non-existent by the fact that we used just pure HTTP. There was no barrier in between a client and the server to maintain that paper trail. So it turned out in the end that there really wasn't one. So although there were some really great successes with this, it turned out that when I went on to do my own thesis project, which is the system I'll talk about next, I was in the situation of having to do something similar. I thought back to the experiences I had, and I realized that this would absolutely never work. So this is a picture of what my actual thesis experiment looks like, which is kind of a mess. So essentially what you're looking at is a big chunk of stainless steel sitting on top of an old superconducting magnet from the 1960s. Some of the equipment in here is sort of a year old. Some of it is literally 50 years old. There's a variety of protocols and a huge number of standards. There's RS-485, there's GPIB, there's Ethernet, there's a number of different things. And the other important thing is that it is a prototype experiment, which means that not only is there a very heterogeneous hardware situation, it's changing all the time. It feels like every week we're getting either a new instrument, or that instrument's no longer necessary, or we need to change the configuration of one of the instruments. And so the old way of doing things, where you had static configurations that never really changed and you needed to stop your server and so on, became such a headache in this particular setup that we went a completely different direction. So when we started looking at this and how we were going to do this, we realized that running this experiment, my thesis experiment, is like a script. There's basically some very discrete steps that you want to check at every point, and then you want to take data, you want to do it again, and then start all over. So you check your experimental health. Is anything on fire? Is this voltage in spec? Are my amplifiers actually on? Things like that. You then, if you fail, obviously you fix it or go home in the worst case. If it's okay, you run in a particular configuration, you switch to another configuration, you then make sure that what you did made sense, and then if everything looked great, you basically start at the beginning. So this looked to me like I should just be able to script this. I want to be able to write Python or something that can actually do this. The unfortunate thing is that I showed you that nice binary protocol earlier that we used to communicate with the devices in Snow, which was just a few bytes and you'd send it over the wire and then things would get understood. Nice JSON RPC at the very top and simple binary at the bottom. That's really not the case with the instruments that I've got presently. So this is the string that I need to send over Telnet to an instrument to get it to read one channel. So I basically have to tell the instrument to clear its state, reset, turn on some particular formatting rules, make sure that the time is absolute, not relative. I need to have units. I need a scan list. I have to trigger it. I have to tell it where the trigger is coming from. And then I can read data back from its internal buffer. It's an absolute nightmare. So writing a simple Python script that manipulates the hardware is just not an option because we have somewhere in the vicinity of 80 different channels and maybe 20 instruments. And I do not want to write code that just sends telnet commands to all these things that are like this. So I wanted to kind of combine what I had done for Snow Plus and what I needed to do for my own thesis work. And the big idea was I want to combine something that looks a little bit like JSON RPC with the paper trail that I would get from a database to be able to expose the interaction between me, the experimenter, and the hardware. This led to an application which is now in production and has been really nice called Dripline. And the basic model for Dripline is that a client interacts with the application by posting a document to CouchDB. And the CouchDB database has this nice changes feed where you can essentially stream the changes that are being made to the database to a client which is listening. The Dripline application is itself listening to the changes feed and thereby can see what changes you've made to the database. It can respond to those changes by interrogating hardware, setting hardware values, and so on and so forth, and then respond to the client by simply updating the document in place. I'm actually going to try to demo this, which very likely will not work. That's the first thing that's wrong. Okay, so here's this CouchDB instance. So I want to tell my system that it's about to get a command. And I want to tell it that I want to get the value of a channel called Hall probe voltage. So we want to read the magnetic field that is present in my experiment right now. So I do this, save the document, and like magic, you can now see that the system in very little time, so it's essentially able to respond so quickly that CouchDB just thinks that the document hasn't even always had this form, essentially. What I got back was something that tells me that there's about 30 Gauss of magnetic field straight, like in my experiment. There's a raw value, there's a timestamp, and so I'm able to basically keep a perfect paper trail of what I did because each command that I send to the system is logged. So to get back to this, the way that Dripline basically abstracts the experiment is the fundamental unit of organization is called an endpoint. So this might be, for example, the Hall probe voltage that I just showed you. It may be something completely different. It's capable of running our data acquisition software as well. So it can do, for example, spawn a sub-process to take data and report back the status of that data taking. The endpoints are grouped into units which are called providers. So the provider for a particular endpoint might be an instrument that has, say, 20 channels in it, and each one of those channels is an endpoint, and that instrument itself is called a provider. The providers are then grouped into nodes, which is exactly the same terminology as an Erlang node. A Dripline node is an Erlang node. And then there's one further sort of layer of indirection, which is the bus. The bus is how data is actually sent to instruments and how data comes back from those instruments. So there is not native Erlang running on these instruments. There is some communication layer that happens over Telnet or GPIB, something like that, that the bus abstracts away. So the client I/O is done by communicating with a CouchDB instance, which then the changes are propagated to a node, and the server I/O is done by the bus. The bus basically interrogates the state of an instrument, and the value is percolated back up through Dripline and is sent to the client. The configuration is also done in CouchDB, so the particular endpoints are actually described by JSON documents. So in this one, you'd see that the type is channel. The instrument, which is essentially what instrument is this endpoint attached to, is ADC mux. There's a locator field, which basically translates the high-level name, which is, in this case, Hall probe voltage, which is that alias field, translates that into something that the instrument can understand. The instrument has no idea that there's a Hall probe attached to it. It knows that on card 1, channel 8, something is attached to it. There's a sensor type, which essentially tells it, are you reading a voltage? Are you reading a current? Are you reading a resistance? And then there are these things called post hooks, which are essentially ways to tell Dripline that the value that it gets back from an instrument is not the value that an experimenter is interested in. So, for example, when I read that Hall probe voltage, that's a voltage, and I don't care about the voltage. I want to convert that to a magnetic field. So there's literally a function, and written in Erlang, that is in a module that is called NMR Hall Cal 77K. It's a calibration that we took of this Hall sensor, which means that when Dripline reads this value back, it will apply that function to the result that it got back from the instrument, and then the final value that you get is actually the value after having the function applied. So it's a nice way to have things like calibrations, if you only care about part of the response, so on and so forth. So to kind of break down what actually happens to give you back this nice, this nice result, the idea was and is to try to provide as expressive an interface to the hardware as you could possibly get. You really don't want to be sending huge strings or things that are not human understandable to the database, because that's just gross. So you want to be able to send queries that look like this, where you just say get and then the name of something. So there's essentially a verb, which could be get, set. There's a run verb, which is used to start a subprocess, for example. There is an info verb, which allows you to ask questions about the Dripline system itself. Is it healthy? Is it running? And then there's an endpoint, which is like a channel or a particular thing that you're interested in about the system. It's also the case that you can send configuration. So one of the nice things about the system is, as I mentioned before, in the past we had these very static configuration files that you had to update like on disk in order to change the configuration of a system. With Dripline, you can actually change the state and the configuration of the system without ever stopping the application itself, because the configuration comes through the changes feed as well. And Dripline will start and stop instruments and buses as necessary to provide the channels that you're asking for. So when we add a new instrument, we don't even need to stop our slow controls. We literally just change a value in a database, Dripline picks that up. The node that is responsible for that particular thing decides whether or not it needs to start any hardware, and then the next thing when you try to ask for that value, it simply goes through the same machinations that it would if it already knew about it and gives you the result. So the way that's actually implemented is fairly straightforward, actually. There's essentially the JSON documents that come across the changes feed go through a parser and semantic analyzer, which is just a JSX callback module. If you're not familiar with JSX, it's a JSON parser for Erlang. It's a great library. It's really nice if you want to perform some kind of semantic analysis in line with parsing JSON, because it allows you to define a callback module for doing just that. So for us, what we want to be able to do is parse the JSON and at the same time change that into an internal representation that our system actually understands. We tried using JSON validators, but it turned out that what we wanted to do was just not a good fit for the validators that were out there. If you fail at that point, then it's simple. You just report the error. So you may say, clearly you don't understand the format of arguments that are supposed to be passed to the system, or you forgot to set a particular field. You just said, you said set, but then you didn't tell me what you wanted to set it to, things of that nature, and that can be reported directly. If that works, then there's two functions that are then generated. The first function is the function to call to retrieve data. So this might be, for example, you need to call this particular instrument module. The function inside that module that you need to call is read, for example, and the argument is whatever the name of that channel is. So this is nice because you go essentially from this high level get Hall probe voltage. After the parsing and semantic analysis stage, what you have then is literally an MFA that you can use with Erlang apply. Once you've generated those functions, and the second function you have is the response function. So the second function is essentially a function that the worker can call to send data back to whoever requested it. At that point, you just spawn off a new worker. You give it the function it's supposed to apply at the beginning and the function it's supposed to apply at the end. It goes off, queries the instrument using the first function, which is of zero arity, and it literally has no idea what it's doing or why. It just gets data back. It then calls that second function on the data, which generates a response which can be sent to whoever called the function, essentially. That then, in general, for example, does something like update a CouchDB document. Or there's actually one of the other plugins that I'm working on right now is for IRC. So you can actually have an IRC bot sitting in an IRC channel, and the result of calling that response function will be to send a message to an IRC channel telling you what is going on, which is just kind of cool. So the instruments themselves, what I ended up doing for these is actually writing behavior modules that deal with the abstraction of the instrument. So I apologize for the wall of text, but I think it's interesting to look at an example. I showed you the sort of disgusting string that has to be sent to an instrument in order to get it to read a value. But what's important to recognize is that even though there are these big strings that need to be sent, in general, there's a very consistent behavior. There's a very consistent interface to hardware. You have a bus. It may be Ethernet. It may be GPIB. It may be something entirely different. But what you do know is that the instrument wants a certain string, or it wants a certain sequence of bits, or whatever. So the instrument modules themselves actually do no communication with the hardware. They only tell the bus modules what strings are supposed to be sent. So what's great about that is writing a new instrument is almost trivial. In fact, it can be automatically generated in most cases. And the modules that you wind up with look something like this. So this is the entire module to control the superconducting magnet controller, which we use in our experiment. It is very short. Basically, you see that's the name of the module is the name of the instrument. So in this case, it's an AMI 420. Its behavior is gen prologic. So it's a generic behavior which is specific to a type of bus, which is the prologix bus. It exports two functions, just basically a handle read and handle write. And then it also just has an init and a start link. It's very straightforward. And this is essentially a wrapper around gen server. So when you get a read, the handle read function is called, of course, and it may be supply current or supply voltage or coil constant. So this is nice because these are very human readable, easy to understand names that actually wind up in your configuration database. So you'd say, I want this channel to be mapped to supply voltage on the AMI 420 instrument. And then when you call that, when you interrogate that channel, you wind up in this function clause. And that function clause says, I want you to send to that instrument over whatever bus, in this case it's the GenProLogics bus, this string. And then of course the state data is returned. And the state data is trivial, it's an empty tuple in this case because you don't need to keep any state. Some instruments have a much more complicated state, so some of the instruments need to cache their results because they are slow and crappy and you can't send too many requests at once because they simply can't keep up. So you want to be able to cache values. So that's why that you want to be able to keep state data around in some cases to handle cases like that. And then at the very bottom you see that if someone tries to write data to this particular instrument, there's an error tuple that's returned that just says unsupported method write. And that is because the superconducting magnet controller is not something that you want people to screw up and be able to write arbitrary values to while you're in production. So where we've gotten with this is we've managed to come up with a system which gives us a really nice extensible framework for communicating with heterogeneous hardware systems, which is built on top of really nice rock solid CouchDB and just Erlang OTP libraries. It's nice because the previous method of taking data was basically me sitting in front of a bunch of hardware, twiddling knobs and making sure that things were working, which after a few days and a few hundred cycles is just exhausting and error prone. It's now just scripted, and it's great because in Python, for example, you can just use CouchDB-Kit and talk to your hardware using very nice existing libraries. And what we've wound up with is a very flexible and dynamically reconfigurable experiment, which is great when you have hardware which is changing all the time. So at present, we have essentially, this is, despite the fact that it is, the library is fairly old in terms of when it was deployed, it's not old in terms of developer time, so I'd like to think of it as an alpha version, but it is in production and it's been working quite well for some time. And Erlang, not only in my thesis experiment, but also in the SNOW experiment in Canada, has proven itself to be an absolute just slam dunk when it comes to managing and configuring, controlling hardware. And I would urge anybody who's thinking about a system like this to definitely think about Erlang. I certainly don't think I'd have trouble with this audience, but some are more reluctant. And so what we've wound up with is a very flexible and powerful tool. Next steps, there's a lot of refactoring that needs to happen. You know, there's this kind of tyranny of working code. If you saw Garrett's talk earlier, there's a lot of discussion about you get to the easy part and then it works. And it's tempting at that point to basically just walk away and say, great, we're done. So Dripline is sort of just past that, where we're getting, it definitely works and it's starting to become nicer and nicer, but there's a lot of work to be done. We want to be able to support, among other things, in-band alarms and notifications. So right now, you essentially need to query the state of the system, check to see if it's good or not, and then go back to the system using out-of-band communication to change things. It'd be nice if in-band, in process, or in Erlang process, you could basically inspect a value and decide what to do if it is if it's out of some specification, and more comprehensive testing libraries. But I also have to graduate somehow, so I'm in my last year or so of graduate school, and so it's really kind of a challenge to find the time to develop this, even though it's really been a lot of fun and really nice. So if anybody is curious or wants to contribute or just look at the code and give feedback, I would certainly welcome that. And thank you very much for your kind attention. Yeah.
How many different bus protocols did you have to implement to make your experiments work?
So at present, there are three. There's just raw Ethernet, where you connect directly to a device and send packets to it. There's the Prologix bus, which the AMI 420 is an example of, where you have an Ethernet to GPIB bridge. And so you have to deal with the bridge in, the GPIB is essentially an old, very much like token ring way for communicating with instruments. It is a terrible map onto Ethernet, but people did it anyway for some reason. And so there was a lot of implementation details there in terms of getting that logic right in communicating with the bridge. And then there's raw GPIB as well, where you're sending commands over GPIB to instruments to get responses. But there are more that are on the way. So we have some custom hardware coming from the shop that we're going to need to implement yet another protocol for, which is going to be essentially serial. Uh-huh.
How do you test the system controller? Do you write simulators for each one of the C interfaces of the devices?
It's been a real challenge to figure out how to test it. So one of the things that I've been playing around with a little bit is using a common test harness and combining that with, I started down quick check, but I then decided to try proper instead for doing some kind of property-based testing of these things. But it's really difficult because in general, it's really hard to simulate instrument responses. And how do you even start to talk about how to do that without absolutely going down the rabbit hole? So it's been difficult to figure out how to do that. I can test most of the configuration stuff, that I update a configuration variable, it should change in the following way. That's straightforward. But testing the hardware has been a real challenge. And I'm still trying to figure out exactly how one does that. Uh-huh.
Have you been able to get other people interested in using your software for their experiments?
Yeah, there's been a couple of other people who have been interested. And so unfortunately, I'm a little reticent to give them something that I'm not sort of 100% like, yes, this is a version that you can work with. So it's going to be deployed on an experiment that's coming up at MIT, but it's a work in progress. So, if people are interested in, contributing to a project that will be used in nuclear physics experiment, because that's kind of cool, then, shoot me an email and let me know. Because it seems like it will get deployed in other systems. But yeah, I found that in general, when I talk to other physicists about the project, at first they sort of think, oh, that's kind of a novelty. It's this weird programming language and they've never heard of it, and what is this really for? But this domain in physics, which we call slow controls, absolutely everybody that I've ever met in physics has nothing but complaints about their slow control system. So when you say that it's really robust and it supports multiple protocols and you talk to a database to communicate with it, people get interested. And so there's definitely been a lot of interest. I'm actually giving a talk tomorrow at Berkeley about this system, among other things. Uh-huh.
So at the beginning you said you just wanted to use Erlang.
Mm-hmm.
Is that because you had significant Erlang experience, or were you learning Erlang and writing this project?
No. When I initially got started down this road, I had no Erlang experience. I knew of the language, but I didn't really have any experience using it. At that point, I had written almost all C and C++, and a little bit of Python. But reading about it, I've always been kind of a hardware guy, so reading about it, I thought this is a great map, because solving problems is so much easier when you have the right tool. When you're working in the right language, solving problems is so much easier. And reading about Erlang, I just thought this is such a great map from the language onto the hardware domain, where you really want to control things in this way. So I sort of learned it as I went. Which means there's some real doozies in the first iteration in terms of what the code looks like. That nowadays I look at it and I'm like, oh my God, that's awful, but it works. Okay, well, thank you.